Hello, RubyKaigi. My name is Peter, and I'm on the Ruby core team, and I'm a senior developer at Shopify. Today, I'll be talking about modular garbage collectors, which is an experimental feature in Ruby 3.4. You can get a copy of these slides by scanning this QR code or by following this URL. Don't worry if you end up missing this QR code, because I'll also show this QR code at the end of this presentation. So a little bit about me first. My name is Peter. I'm currently based in Toronto, Canada. I'm on the Ruby core team, and I'm a senior developer at Shopify on the Ruby infrastructure team, where I work on performance and memory management in Ruby. I'm the co-author of the variable width allocation in Ruby, which improves performance and memory efficiency of the Ruby garbage collector. I'm also the co-author of the Ruby free at exit feature, which frees memory at shutdown to allow the use of memory leak checkers such as Valgrind or macOS Leaks tool. I'm also the author of the Ruby memcheck and autotuner gems, and in my free time, I like to travel and take photos, and I post them on Instagram at peterzoo.photos. So I'm going to give a brief overview of this talk first. So first, I'll be talking a little bit about Ruby's Mark Sweep compact garbage collector. Then I'll be talking about the missing features from this garbage collector and the motivation of introducing alternative garbage collector implementations. Next, we'll be taking a look at the modular garbage collector feature in Ruby 3.4, which allows us to use alternate garbage collector implementations inside of Ruby. We'll be taking a look at how the garbage collector communicates with the Ruby virtual machine using the Modular GC API, and briefly look at how to build Ruby with Modular GC enabled. And then we'll take a look at how to build the two garbage collector implementations that ship with Ruby. And finally, we'll be taking a look at MMTK, which stands for the Memory Management Toolkit. This is the first user of the Modular GC that is not the built-in GC in Ruby. We'll look at the features that MMTK supports and the implementation of MMTK through the Modular GC API. And then we'll take a look at the future roadmap of MMTK and Modular GC. Let's first take a quick look at what a garbage collector is. So at a high level, the garbage collector is responsible for three things. It first performs object allocation. When you create a new object, for example, a hash or an array or a class, Ruby requests a piece of memory from the garbage collector. And then during the allocation of the object, the garbage collector can choose to run a garbage collection cycle to free up some of that memory. So it is now responsible for determining which objects are alive and which objects are dead. There are many techniques for doing this, and Ruby does this using tracing, by tracing object references from root objects. Root objects are things such as global variables and constants inside of Ruby. After determining the liveliness of objects, the garbage collector reclaims objects that have died. And this includes reclaiming resources of objects, resources of the object, such as memory allocated from the system, closing file descriptors, and running finalizers. And once the object has been reclaimed by the garbage collector, this memory can be reused by the garbage collector for a new object. So to allocate object, Ruby uses a free list allocator. And how the free list allocator works is very simple. It's just a linked list of empty memory that we can allocate into. For example, here we have a Ruby heap with space for 6 objects. We have 3 objects that are allocated here, which are of type string, array, and regular expression. And we have 3 empty slots here that we can allocate objects into. For the free list allocator, we build a linked list of slots just like this. And then when we need to allocate an object, then it allocates into the head of the free list, and we move the free list to the next element. And then we can repeat this until all of the slots have been filled up. And then once all of the slots have been filled up, what do? We run a garbage collection cycle to reclaim any dead objects. Ruby uses the Mark Sweep compact garbage collector, which, as the name implies, has 3 phases. First, we have the mark phase, which determines which objects are alive, the sweep phase, which reclaims all of the dead objects, and the optional compact phase, which moves objects so we don't have holes or fragmentation in the memory. So now I'll show the marking phase using an example. So here we have an example heap from the previous example. And let's add object references here, where arrows indicate that a particular object refers to another object. And we have the root objects here, which include things like constants and Ruby objects on the stack. So we start marking from the roots, and the objects that have been marked but not yet traversed are marked gray. So let's pick the gray object here. And so here, let's pick the array. And let's traverse the children of the array. And we mark this array as black, and we mark the children of the array as gray, which is the object in this case. The class here is already marked gray, so there's nothing we need to do. And then let's pick the next gray object, which is the class. And since this class refers to no objects, there's nothing we need to do. And now let's mark the gray object black, and mark its children, which is the string, and then we mark the last gray object black. And since this object has no children, there's nothing we need to mark. And since we no longer have any more gray objects, this marking phase is now complete. And so after the marking phase, all of the black objects are alive, and all of the white objects are dead and can be reclaimed by the garbage collector. So let's go back to this example. So for the marking phase, we scan the heap, and we reclaim any white objects, and we have 2 here. So the garbage collector will also reclaim any additional resources of the object, such as memory allocated from the system or open file descriptors. Compaction is an optional phase of garbage collection that can be manually enabled. It moves objects around the heap so that all of the objects are towards one end of the heap, and this can help us save memory because it prevents issues known as internal fragmentation, which is where chunks of unused memory is interleaved with used memory and prevents memory from being freed, which increases memory usage. Ruby uses the 2-finger algorithm for compaction, and let's see how that works using the example heap. And as the name implies, there are 2 fingers or cursors. So from the left, we have the free cursor. This cursor moves from the left to the right until the first empty slot. So here it moves to the right to the first empty slot. And then from the right, we have the scan cursor, which points to the first live object in the heap. Then we swap the objects at these 2 locations, and we leave a temporary object at the original location known as a forwarding reference. And we'll see how this is used in the next phase of compaction. We then move the free cursor to the right onto the next free slot, and then the scan cursor to the left to the next live object. But since the 2 cursors have now met, this phase of compaction is complete. We then enter the reference updating phase, and here we modify references from objects that refer to a t-moved object. So let's add the object references back. We now linearly scan every object and find objects that refer to moved objects. We can see that this array here points to a t-moved object, and we can update this reference to point to the new location for the object. And then we can continue scanning the remaining objects, and then once we finish that, we can reclaim all of the t-moved objects. So that was a brief and simplified introduction to how the mark sweep compact garbage collector works in Ruby. There are many optimizations and implementation details that were omitted from this introduction. So I have a blog post here linked that describes how the garbage collector works in much greater detail, and please check it out after the talk if you're interested. So we already have a garbage collector in Ruby that's been continuously improved upon for the past 30 years. It works and provides decent performance. So now let's take a look at some of the features that the Ruby garbage collector is missing. So Ruby's garbage collector uses the mark sweep compact algorithm, which is a fairly simple algorithm to implement and understand. But there are many other garbage collection algorithms that can provide higher performance. So one garbage collection algorithm that is used by some languages, such as Python, is called reference counting. Reference counting keeps track of the references from one object to another, and so when it detects that an object no longer has references to it, it is dead and can be reclaimed by the garbage collector. We can almost use this in Ruby. However, this requires that we can accurately keep track of when references from an object is added and removed. This is implemented in Ruby using a concept called write barriers. These are callbacks to the garbage collector when an object adds a reference to another object. However, the implementation of write barriers is incomplete in Ruby because it was not designed with reference counting in mind. For example, there are many cases where removing a reference from an object does not fire the write barrier, which would make reference counting not work properly. You will notice this many times throughout this talk. By having the same garbage collector algorithm for the past 30 years means that there are ingrained assumptions about how the garbage collector works in the Ruby VM. And this prevents flexibility in the garbage collection algorithm that we can use. So right now, we cannot use reference counting in Ruby. Semi-space copying garbage collector has two regions of memory, which are called the from space and the to space. We allocate in the from space until we run out of memory, and then we run a garbage collection cycle by moving all of the live objects from the from space to the to space. And let's see a quick example of how this works. So we allocate objects in the from space using a bump pointer allocator, which means that we allocate objects from the top and move the pointer forward. And then when we fill up the from space, it is time to run a garbage collection cycle to free up space, and let's mark the live objects as black here. We then move the live objects to the to space, and then we can reclaim all of the memory from the from space, since we know that all of the objects in the from space are dead. We then swap the from space and the to space, which guarantees that we always allocate objects into the from space. And so it should be clear what the advantages of this algorithm is. So every garbage collection cycle defragments the heap, so it has compaction built in. However, this ends up using twice the amount of memory, and this is definitely a case where we trade performance for higher memory usage. However, again, we cannot use this algorithm in Ruby, because Ruby requires that the GC algorithm supports pinning, which is where certain objects cannot be moved. But semi-space copying requires that all live objects must be able to move, so we cannot use semi-space copying right now. IMIX is a garbage collection algorithm that combines ideas from mark and sweep and semi-space copying. IMIX splits the heap into many blocks, and using heuristics, it determines which blocks are most likely to be fragmented. Then during marking, it moves live objects in blocks that it determines to be the most fragmented. This gives us the benefits of semi-space copying because it moves objects during marking and allows for pinning support because not all objects are required to move. So we can use this algorithm in Ruby. Another feature missing from Ruby's garbage collector is parallelism. As we probably know, with the exception of reactors, Ruby does not support parallelism. So multiple threads in Ruby don't run at the same time. This simplifies the implementation and can prevent race conditions. However, the CPUs in modern machines have multiple CPU cores, and we are not taking advantage of that. Also, if you were in Koichi Sasada's talk earlier today about reactor local GC, you might know that the GC is currently shared between reactors. And because of that, when we run a garbage collection cycle, we need to pause all of the reactors, so it ends up becoming a bottleneck. So by making the garbage collector parallel, we can improve performance for Ruby applications and make it less of a bottleneck for reactors. For the longest time, every object in Ruby was exactly 40 bytes in size. Any additional memory was allocated through the system using malloc. This was done for simplicity because it avoided internal fragmentation. However, it was inefficient for memory usage because there was additional space required to store pointers to other regions of memory. And it was also bad for performance because it required more memory reads to access the data for the particular object. So in Ruby 3.2, I co-authored variable with allocation, which allowed the garbage collector to allocate dynamic slot sizes. However, due to technical limitations, we are limited to 5 slot sizes, which are powers of 2 multiples of 40 bytes. This means that the slot sizes are 40 bytes, 80 bytes, 160 bytes, 320 bytes, and 640 bytes. Any objects that require more than 640 bytes in space would have that additional memory allocated from the system via malloc. Through this feature, we saw 2 to 10% performance improvements in various benchmarks. Other garbage collectors are able to implement truly dynamic slot sizes without the slot size limitation that variable width allocation has. So then this will allow us to be able to further improve performance and decrease memory usage. So now we've seen some of the reasons why using a different garbage collector implementation could improve performance for Ruby. So you might be asking why we don't just rewrite Ruby's garbage collector. So we chose to not replace Ruby's current garbage collector for several reasons. All of the garbage collectors are a trade-off between performance, memory usage, and complexity. Ruby's mark and sweep garbage collector is great at reducing memory usage and has relatively low complexity. Ruby programs range from small scripts that take milliseconds to run to web applications that serve a huge amount of requests. So there's really no garbage collector that is one size fits all. Ruby's current garbage collector is also very battle-tested and provides a good balance of performance, memory usage, and stability. So we don't want to replace it. And also, if we did replace the Ruby garbage collector, and then in the future we wanted to switch to an even higher performing garbage collector, we would need to repeat this process all over again. So to solve this problem, we are working on modular garbage collectors. This allows the user to switch garbage collector implementations depending on their requirements and workload. This was released as an experimental feature in Ruby 3.4 and implements an API to implement alternate garbage collectors and a mechanism to load them into Ruby. This feature was introduced in ticket 20470, and you can read it if you're interested in more details. The first part of this feature involves splitting Ruby's garbage collector into two parts. Previously, Ruby's garbage collector lived in a file called gc.c, which was compiled into the Ruby binary. So we first split this file into two. The existing gc.c file no longer contains any garbage collector implementation. Rather, it only interfaces the Ruby VM for the GC. And so this does things like start and stop reactors for running garbage collection cycles. This new file, which is under the GC directory called default.c, contains the actual implementation of the mark and sweep GC that is in Ruby. This allows us to build the default GC separately from the Ruby binary. And then the GC implementation is loaded into Ruby as a shared library, similar to how native extensions are loaded. And then the communication between the default GC and Ruby is done through the modular GC API. The GC implementation communicates with Ruby through the GC API. This API contains two parts: the API that the GC implementation is required to implement, and the API that the GC implementation is allowed to use in Ruby. This header file contains the function prototypes for all of the functions that the GC implementation is required to implement. This file lives under gc/gcimpo.h, and there are about 60 functions split across 14 sections. And let's take a look at some of these in greater detail. So the first section are the boot up functions. These are ran at boot to allocate data structures for the garbage collector and perform setup. There are many functions here because there are various boot up phases in Ruby. So we have object space allocation, which allocates the data structures for the garbage collector. And this is ran before the VM has booted because we need a functional garbage collector for the VM to boot. We also have functions to allocate data structures for reactors, and another initializer function that is ran after the Ruby VM has booted, which allows the GC to define methods and do other operations that require a functional VM to work. We also have shutdown functions, which performs cleanup and frees data structures in the GC. We also have functions involving running a GC cycle, such as manually running a GC, disabling and enabling the GC, and setting configuration. We have object allocation, which asks the GC for an object of a specific size, and then the GC returns a pointer to the object that was allocated. And we have functions for the GC to mark an object as alive and to pin an object to ensure that it does not move. And we also have write barriers, which are callbacks so that the GC know when an object has a new reference to another object. So that was the API that the GC implementation is required to implement. So to ensure that the GC implementation has abstraction from Ruby internals, the GC implementation is only allowed to use the public Ruby C API and this list of functions. This is defined in gc/gc.h. This has functions that are not exposed through the C API that the GC implementation may want to use. And let's take a look at some of these in greater detail. So we have functions for locking and unlocking the Ruby VM, as well as functions to stop reactors. This is needed to run garbage collection cycles because right now reactors cannot run while a garbage collector is being run. We have functions to mark the child objects of a particular object. Remember, the GC implementation is responsible for doing the marking, but the GC implementation is not aware of how Ruby objects work internally. And so it is the responsibility of the Ruby VM to walk the references of an object. So this allows us to change how the data structures of Ruby objects work without needing to change the GC implementation itself. We also have a function that is called after the GC has determined that an object is dead, and this is called before the object is recycled by the GC. So then Ruby can perform cleanup such as freeing memory or closing file descriptors. So we've now seen a brief overview of how the Modular GC API works. To build it, you can follow the guide in the linked README. Here's what it looks like. It explains the steps to build Ruby with Modular GC enabled, how to use the two GC implementations how to build the two implementations that ship with Ruby, and how to use them. The two implementations that ship with Ruby is the default GC and MMTK. The default GC is the GC that comes with Ruby, but you can modify it, build it separately, and then load it into Ruby. MMTK stands for the Memory Management Toolkit, and I'll talk about that in the next section. So this is part of the Modular GC work. We are working on the first user of the Modular GC API that is not the default GC. The first user is MMTK, which stands for Memory Management Toolkit. It's a language-agnostic framework of garbage collectors. It is written in Rust and is developed by the Australian National University. MMTK contains a collection of garbage collection algorithms, and once a language plugs into MMTK, we can use a wide variety of GC algorithms. MMTK is currently integrated with many languages, including Java on the Gixar VM and OpenJDK, Julia, V8 JavaScript runtime, and of course, Ruby. So let's take a look at some of the features that MMTK provides. So as I mentioned before, MMTK provides a wide variety of GC algorithms, which it calls plans. Depending on how much of the MMTK binding that you've implemented, you may only be able to use some of these plans. So first, there's no GC, which as the name implies, only allocates objects and never reclaims them. This is useful for testing that object allocation works without needing to implement any garbage collection. MMTK also has the mark and sweep garbage collector, which is similar to how the one in Ruby works. And this is the simplest garbage collector that collects garbage but doesn't move any objects. We have mark and compact, which is similar to Ruby's garbage collector with compaction enabled and moves objects around to reduce fragmentation. We've also briefly discussed semi-space copying before, and MMTK also has this, but it also doesn't support pinning because all of the objects must be able to move. Immix was also briefly discussed earlier. This is a higher performing garbage collector that supports pinning, and there is a work in progress implementation of LXR in MMTK. This is currently only integrated with the OpenJDK, and LXR stands for Latency Critical Immix with Reference Counting. It uses reference counting for performance on reclaiming dead objects and immix for object movement to reduce fragmentation. The team saw significant performance improvements when using LXR over the default garbage-first garbage collector in the OpenJDK. MMTK natively supports parallelism by using a concept called work packets. Each work packet contains isolated work that can be done on a different thread. And so then multiple threads can pick up different work packets and then perform tasks in parallel. So there are currently two implementations of MMTK for Ruby. So the original implementation of MMTK in Ruby was implemented by the MMTK team. This work started in 2020 and continues to this day. They use a fork of Ruby and has implemented novel ideas such as sidecar objects to reduce the amount of memory allocated from the system, the concept of potentially pinning parents to increase performance for object movement, and combining marking and object movement into a single phase. With the introduction of Modular GC, we're porting over work from the MMTK team's implementation and implementing it on top of Modular GC. So far, we've implemented no GC, mark and sweep, and non-moving immix on Modular GC. So the source code for all of this lives in the Ruby/MMTK repository, and please check it out if you're interested. So let's see at a high level how MMTK is plugged into Ruby using the Modular GC API. So inside of the MMTK bindings, we have a layer that is written in C that interacts with the Modular GC API in Ruby. The C bindings here provide an extension of Ruby for MMTK and provides implementation for things such as stopping the Ruby VM, marking an object, or freeing a dead object. The C bindings in MMTK then interact with bindings written in Rust. And then the Rust bindings interact with MMTK core. MMTK core here is installed as a cargo dependency, and MMTK core is written in Rust. MMTK core contains the actual underlying implementation of the garbage collector, but the Rust bindings in the Ruby/MMTK repository provides extensions to MMTK core for Ruby, and implements things like defining work packets for marking and freeing objects. So we've only worked on the modular GC version of MMTK for less than a year. We're still currently far behind the MMTK team's implementation, and because of this, we are much slower than their implementation. And we are also quite a bit slower than Ruby's default GC as well. And here are some of the features that we are working on that will significantly improve performance. So right now, we only support non-moving plans, such as mark and sweep and non-moving imics. So we're adding support for moving plans that will allow imics to move objects, which will improve performance and reduce memory usage. So one detail I did not talk about the Ruby garbage collector is that it is generational, which means that objects are young when they are first allocated and become old when they survive for a long time. This speeds up the garbage collector because we can run a garbage collector that only scans young objects since they are most likely to be dead. MMTK supports generational garbage collector through plans such as sticky imics, which implements a sticky mark bit to only scan newly allocated objects in a garbage collection cycle. MMTK operates on units of work packets. So the more that we can split the work into smaller packets, the more MMTK can take advantage of parallelism and thus improve performance. Since Ruby's garbage collector has been single-threaded up until now, there has not been any work on making various phases of the garbage collection thread safe. For example, you might expect that we can free two different dead objects on two different threads, but the two different objects may be accessing common data structures and thus have race conditions. So in conclusion, today we took a look at how the Ruby garbage collector works, the motivation and implementation of modular garbage collectors, and the MMTK integration with Ruby. If you're interested in building your own garbage collector, you can do that today with Modular GC. Note that this API is experimental and subject to change, so don't use it in production just yet. I'm looking forward to seeing what you can build. You can find a copy of these slides at this QR code. If you have any questions, feel free to ask me after this talk or through email or through social media. Thank you for coming to my talk.